Hey everybody, welcome to week 10 of PS398. I'd say that it's hard to believe that we're this far along, but just think about everything that we've talked about up to this point. Remember that one of the weeks we talked about what a set is, what a function was. And now here we are using these things for all sorts of cool things. And I think that today's lecture is going to be a really cool one to show you how these tools come together that teach us some really important lessons about international relations. So in the previous lecture, we introduced this concept of time into our fables. Presumably you already were aware of the concept of time. It's been happening to you for some amount of time now. But the way to think about it, or the beginning of a way to think about how to use it analytically, that's a different story altogether, right? And I think that we saw that in these strategic worlds that we construct, in these fables that we write down, time is a really interesting tool for us to use. From a narrative standpoint, time is a great way for us to dig in and to create some Aristotelian tension. But from an international relations standpoint, time is a good way for us to understand how strategic actors under anarchy operate with some amount of distrust afoot. And what's great about the fabling enterprise is that what makes tension for us as writers of fables, and what makes the countries that we're modeling feel tension, what are their trade-offs, those are the same things. Right? These stories actually allow us to, by doing what is best for us as authors, sometimes we're able to get to the bottom of what's going on for real people that don't think this is such a storyland sort of thing. So this time wrinkle really made it obvious that we fable writers have real opportunity to learn a lot about the real world factors that decision makers experience at the international level. We didn't tell the ending of any of those stories, though. I'm not going to have to motivate today's lecture very much because you just finished watching a bunch of videos about the rule of law game and the deterrence game and the ultimatum game, and just like we did with the games lecture, we didn't finish any of those stories. All we did was say once upon a time a bunch of times, where then we had a sense of time to be able to say once upon a time about. There wasn't even once upon a time in chicken. There was just chicken. This introduction is just going great. But I think that you'll see the way that we get to the ending in these time-respecting stories, in these extensive form games, the way that we get to the ending of these things is itself kind of interesting. Just the same way, and we went pretty fast, so it might not be obvious. So in Nash Equilibrium with simultaneous move games, there were substantive commitments, right? What a Nash Equilibrium is a substantive commitment. You don't just... It's very annoying when somebody just writes down a game and just gets the Nash Equilibria, and then you say, okay, and what does that mean? And you say, well, I wrote down a game, and so my next step is to get the Equilibria. There were substantive commitments made along the way. Mutual best response, no incentive to deviate. Those are substantive commitments, right? And similarly, what we talk about today in terms of sequential rationality, that's a substantive commitment. And so the tools of analysis that we use are themselves substance-laden. I don't want to say value-laden or theory-laden. I guess they are theory-laden at least. So what you're going to be taught today isn't just how to analyze these games, it's a set of substantive commitments that allow for a particular kind of analysis to transpire. And if you ask me, it's a very useful style of analysis. The analysis of perfection. Sequential rationality winds up being aligned to the notion of perfection, which we'll discuss in the B and C blocks of today's lecture. The only reason to have an introduction more than 2 minutes is that I really want you to, I hope you won't just view this as just, and here's what you do. This is what you do, but it's what you do for a reason. And I hope that I'm able to convince you that those reasons are good, but also I want to remember to try to tell you what those reasons are as we go. So I think that this will be a good day for us to think very hard about the notion of credibility and what it looks like in the context of sequential rationality, which promises to be a good overarching theme for the lecture. So I actually want to talk about the issue of credibility in 3 different contexts. I want to show you 3 different models, and along the way we'll introduce the tools for analyzing extensive form games, and hopefully we're able to touch on this credibility and sequential rationality topic from 3 different angles in a way that really helps you understand what we're talking about here. So in the A block, I want to talk about the simple deterrence model that we introduced in the A block of last week's lecture. How do we get to a prediction, right? What is a predicted outcome in an extensive form game, and how do we obtain one? So just the same way that we had to turn chicken into predictions, or Bakker-Stravinsky into predictions, or matching pennies into predictions, so too do we have to generate some predictions using these extensive form games, but we don't yet have a method for doing that. So in the simple deterrence game that I'll be showing you, it's a simple matter of what might be intuitive for you, the backwards induction algorithm, which is a special case of the larger subgame perfect equilibrium algorithm that we'll discuss later on in the lecture. But I think that even just in the super simple block A sort of thing, you'll see that the role of time is critical in determining when a threat is sufficient to deter a would-be attacker, a would-be nasty thing doer. When does the promise of future punishment deter them from doing something nasty today? In the B block, I want to extend the deterrence model by talking about a model of, you guessed it, extended deterrence. So what happens if a third party observes a potential tension between two other states? So if I'm the United States and I see tension somewhere else in the world, perhaps tension that would be bad for my overarching foreign policy, what can I do to try to stop that conflict from happening? How does a third party extend treaties in a way that reliably, if at all, stops war from happening? So now the idea isn't just deterrence. It isn't just, am I strong enough to get rid of the bully? Now the question is, do me and my new friend that I signed an alliance with, is that strong enough to team up and keep the bully at bay? So extended deterrence is all about it's not just the two parties in question anymore. When can a third party influence the future by making shrewd diplomatic decisions today? That's a pretty cool thought, right? And then in the C block, I want to revisit the rule of law game that we discussed last week and find its subgame perfect equilibria. I want to show you what Weingast's notion of this model of the rule of law, how this all plays out. What's the ending, or what are the endings? What are the predicted outcomes in that model that helps us to better understand the role of the state? So we're going to be talking about interstate politics in terms of deterrence, extended deterrence. We're also going to be talking about domestic politics in terms of the rule of law. Credibility plays a big role domestically. It plays a big role internationally. Once the aliens come, it will play a big role interplanetarily. Credibility is critical. Credibility is at the heart of time-sensitive international politics under international anarchy. And so today's lecture, I hope, will help you to see some of the really interesting tensions that emerge in sequential rationality playing out between parties whose incentives might not be aligned in a way that leads to happy endings. My sense is that even though we'll be talking about a lot of different analytical ideas, this should be somewhat intuitive for you, and I hope that you get a chance to have some fun with this as well. Your problem set should be, famous last words, relatively straightforward. It might be tedious, you might have a lot of things to check, but we're getting to the point now where you're only annoyed with problems that I ask you, rather than you're not melting existentially, which is a good start, right? So it should be a pretty fun one. Let's get started. So I want to start by showing you the backward induction algorithm as it applies to the simple deterrence game that we introduced last week. So in order to make that happen, we should probably just queue up that deterrence game. So just to rehash what happens in this model, remember, at the beginning of time, country A will say, today it'll be A's and B's instead of 1s and 2s. So at the beginning of time, country A can either not issue any challenges, don't do anything nasty, behave well, yeah, and that'll take us to a status quo node today. So that's the end of time. You can just opt out. You can just say, I'll take the status quo. Or country A can issue a challenge. They can do something meddlesome. They can do something nasty. They can drive their troops to the border of country B. They can attack some ally. They can engage in nasty financial politics. And if they do that, then country B will have a chance to respond. So country B can either acquiesce to the challenge. They can say, you know what, actually, that's fine. we're not enthused about this, but here, take a happiness point from us. Or they can fight back. You can say, you know what? Name a day and time. I'm tired of this. Why are you always so nasty all the time, Country A? Every time with you. And remember that we've got, for the status quo terminal node, we assigned payoffs 3 for Country A and 3 for Country B. For the capitulation terminal node that happens after a challenge and an acquiesce, that's 4 for Country A and 2 for Country B. And for the war outcome, we're calling that 1 for Country A and 1 for Country B. So again, we have a relatively complete story about a simple deterrence model. This is a simple concept of deterrence. Does the prospect of war deter Country A from issuing a challenge in the first place? Before we talk about sequential rationality, let's compress this game. Let's go to the compressed version. Let's go to the strategic form version of this game by depicting it as a matrix. Okay? So Country A is now row player. They can either challenge or not challenge. And Country B is column player. They can either acquiesce or fight. Regardless of what Country B does, in the not challenge row, it's 3-3. So 3-3 and 3-3. If Country A challenges and Country B acquiesces, that's 4-2. And if Country A challenges and Country B fights, it's 1-1. Let's observe that this game has 2 pure strategy Nash equilibria. Right? So you can just throw in some asterisks here and you'll observe that there are 2 pure strategy Nash equilibria. There's the one where Country A doesn't challenge and Country B fights. We'll call that the orange equilibrium. And there's another equilibrium where Country A challenges and Country B acquiesces. We'll call that the blue equilibrium. In the comfort of your own home, you could also demonstrate that this game has a third Nash equilibrium in mixed strategies, but it's not very interesting. We're going to stick to pure strategies most of the time from here on out. And you're like, oh, that sounds great. So we've got these 2 candidate Nash equilibria, the orange one and the blue one, and I'm going to tell you in advance that only one of these is going to be the predicted outcome of our model once we analyze in a way that appreciates time. Notice that we just analyzed in a way that didn't appreciate time. We just used regular old vanilla Nash equilibrium as if this game was simultaneous. But it's not simultaneous, it's sequential. And only one of these predictions is going to be the ultimate prediction of our model once we analyze in a way that respects time. So pause the video and figure out which of these 2 equilibria, the orange equilibrium or the blue equilibrium, which of these 2 do you think is going to be the one that plays out and why? Pause the video. So the screwy equilibrium, if you ask me, is the orange equilibrium. So look at this. So in the orange equilibrium, Country A is not challenging and Country B is fighting. Right? And so in a sense, what's happening here is we're saying the threat of fighting up here in the hypothetical world, we don't get to, we never come here. We never come here. Right? So if Country A is opting out by not challenging, then everything that happens up here is a hypothetical. We don't get to know. We have no idea. Right? And so what we're saying, the logic of the orange equilibrium is this threat of fighting in the hypothetical world was enough to deter Country A, and so they decided that they would rather just opt out and take the reality of the status quo node. However, observe that the thing that is making Country A want to opt out is the threat of war from Country B, who you'll notice has no interest in fighting this war, actually. You'll notice right now, if we got to this hypothetical world, then Country B would be fighting and getting a payoff of 1. However, in this world, they would rather deviate, because they could just acquiesce and wind up with 2, which is strictly better than 1. So the threat of fighting is not credible. In this Nash equilibrium, this orange Nash equilibrium that doesn't respect time, that doesn't take into the fact that all the threats that create a best response have to be credible threats. In this orange pure strategy Nash equilibrium of the simultaneous cousin of this game, we don't take credibility seriously, and so consequently, this threat is allowed to matter in a way that it really shouldn't. Right? If you are country A, you're thinking to yourself, well, you know what I don't want to do? I'm going to take the status quo, and I'm happy about this because country B is fighting. And if I went up to that hypothetical world, country B would fight. Wait a second, but then they would actually have to fight. They would actually have to do that. They would actually have to do it. They would actually have to drive the tanks. It's not just a matter of saying, oh yes, I fight. In the hypothetical world, that isn't what we're talking about here. If we're going to take time seriously, then it's not just a matter of drawing game trees that take time seriously. It's a matter of taking our concept of rationality and refining it in a way that makes this threat not matter. Right? Notice that there's no such problem in the blue equilibrium. So in the blue equilibrium, country A is challenging, and then country B is doing the sequentially rational thing to do at their decision node, which we now hit, and they're acquiescing. Okay? So the question is, how do we properly, what's an algorithm that takes us from a tree to an equilibrium that I don't start yelling about? I don't think that you have to be a specialist to see that the logic of the orange equilibrium is weird and the logic of the blue equilibrium is consistent. But how do we come up with a method that always generates equilibria that I don't have veins popping out of my head, right? And that's the backward induction algorithm in an introductory sense. The backward induction algorithm is going to provide us with a method for turning game trees into choices, into series of choices throughout the whole tree that complement one another, so that what happens off the path in the world of hypotheticals complements what happens on the path, but everything is sequentially rational. So the backward induction algorithm is actually relatively straightforward, especially in an introductory game like this, where there aren't any information sets that have multiple. So technically speaking, there's a singleton valued information set, and there are two information sets. It's just that everybody knows exactly where they are. In the B and C block, we're going to have to amend this notion to be able to accommodate bigger information sets. But as we sit right now, this is actually pretty straightforward. Backward induction proceeds in a limited number of steps. So step one is going to be to take all the terminal nodes, all right, and label them as solved. So I've got 3 terminal nodes, status quo, capitulation, and war. I'm just going to label them all as solved. And you're like, why are you doing that? You'll see. So those are now solved. Step 0, all the terminal nodes are solved. This method only works in these finite horizon games where you can see all the terminal nodes, where you can see every ending. This works in games that you can see like this. In the coming weeks, we're going to have to amend this idea, but the logic will follow through. Step 2, find all decision nodes, which are followed only by solved nodes. What do I mean followed by? Followed by means there's an edge going to it. So notice the country A's decision. They've got 2 edges coming out of it. The don't challenge node goes to the status quo terminal node, which is solved, right? However, if they challenge, that goes to country B's decision node, which hasn't yet been solved. We only labeled the terminal node solved. So this decision node doesn't go only to solved nodes, all right? However, country B's decision node, if they acquiesce, it goes to the capitulation terminal node, which is solved. And if they challenge, it goes to the war terminal node, which is solved. So no matter what happens, we go to a solved node. That's the last decision. That's a late decision. A late decision is one that goes to the end of time, no matter what happens there. Okay? So we go to a decision node that is followed only by solved nodes. Our next step is to solve it by figuring out what we think will happen there. Okay? So let's just zoom in on country B's decision node. Let's just zoom in on this decision. Here we are. This is where the magic is happening right now. We need to know what is the sequentially rational thing for country B to do if we hit this decision node, which is an if. We don't know that we will. We might not. But we still have to think it through so that even when it's a hypothetical, it doesn't get me yelling at you, right? Hypotheticals can make us angry. We need to make sure we get the hypotheticals all just as right as the real things. Otherwise, what happens off the path won't be complementing what happens on the path. So here we go. Notice that country B, they can either acquiesce and get 2 happiness points, or they can fight and get 1 happiness point. Well, 2 is more than 1, so they would rather acquiesce. So I'm just going to highlight this edge. And the idea here is that this node is now solved. We now know what we think will happen here. This decision node, there's no intrigue left. We've thought it through. We've said, okay, well, what will happen at this decision node is country B, if we get here, is going to acquiesce because that leads to their highest payoff, right? So we can just take this payoff and just take it straight to the node. We can just cut all this off. This is all just waste at this point in time. We can just cut it off and just put the payoff, put that 4-2 right on country B's decision node and call it solved. This is it. This is done. We're done. This node is now solved. We can pretend like this was a terminal node. This is officially what looking down the tree looks like. This is looking down the tree. The final step with simple backward induction, like you see in a game like this, is to repeat that process until all the nodes are solved, right? So now that that node is solved, now we have to find another decision node that is followed only by solved nodes. Well, there's only one decision node left, the root node, the beginning of time, controlled by country A. Now, observe that all of country A's edges, this decision node goes only to solved nodes. It can take us to the status quo terminal node, which was solved by definition. In step 0, we solved that, right? Or it can go to country B's decision node, which we now have solved. Now that's just a terminal node at this point in time, right? So if we zoom in on country A's decision, observe, they can either not fight, not issue a challenge, and that takes us to the status quo just as ever, and it gives country A 3 happiness points. Or country A can issue a challenge on the understanding that they can reasonably expect country B to acquiesce. They looked down the tree and they said country B is going to acquiesce to this challenge. Why? Because it was 1 versus 2. This isn't like hyper optimism. They were thinking about what country 2 was thinking from country 2's point of view, right? So they're saying, I can get 4-2. If I go here, there is no credible reason for me to believe that a war is going to happen. It's not a credible threat, and so I issue the challenge. This node is now solved. All nodes are now solved. We have completed our backward induction analysis. So now we can zoom out and notice that what happens is an equilibrium path of play has emerged. That path begins at the root node. It begins from the beginning of time. At the beginning of time, country A issues the challenge. Country B acquiesces, and we wind up at the capitulation terminal node. So that's our predicted outcome. Notice that this backward induction surviving profile is precisely the blue equilibrium. So I want to highlight the fact that everything I'm going to show you today, backward induction and subgame perfection, they're all going to take our existing notion of Nash equilibrium and they're going to refine it, where by that I mean we're not going to come up with any predictions that wouldn't be Nash equilibrium. So everything that we find would have been a Nash equilibrium in the big game if we treated that game like it was simultaneous. It's just that once we introduce this time structure, that whittles the set of plausible predictions down from maybe 2 pure strategy Nash equilibria to 1 unique backward induction surviving profile. An interesting question then is, how would you change the model in order to get deterrence to work? So as things sit, the blue equilibrium was the one where deterrence didn't work, and the orange equilibrium was the one where it worked, right? And what we didn't like about the orange equilibrium was that deterrence only worked because a threat that should not have been credible was treated as if it was credible. So an interesting question is, how would you change this model? What would you change of this model in order to make the orange equilibrium or something like it? What happens? You can pause the video again. You only need to make one change. You need to change one thing on the screen right now. One and only one thing will make will make country A not want to challenge? What's the thing that would do that? Is it something about country A? Is it something about country B? Both? Neither? What? What would you change? How would you make deterrence work in this model? Pause the video. Got it? You would change one and only one thing. You would change country B's war payoff, or country B's acquiesce payoff. So what you do is you say, well, country B, if they fight, they don't get 1 happiness point, they get 3. Or anything more than 2. Yeah? Because now, let's think this through again. So again, call only the terminal node solved. Let's unsolve all the decision nodes. Let's zoom in on country B's decision. Notice, now, country B can either acquiesce and get 2 happiness points, or fight and get 3. They would rather fight. So now we'll highlight that node, edge, we'll highlight this edge, right? So now we call this decision node solved, except now it's solved in a way that leads to the fighting. Now the threat is credible. Now the threat is credible. Let's zoom out and zoom back into country A's decision node. Well, country A can either not challenge and take the status quo, which yields 3 happiness points, or they can issue a challenge under the reasonable expectation that country A will fight and they get 1 happiness point. They would rather take the status quo now. Notice that what made deterrence work had precisely nothing to do with country 1's payoffs. It was not about country 1's payoffs. It wasn't about how awful we made war. It wasn't about how awesome we made acquiescence. It wasn't anything about country 1 once we got to the hypothetical world. That is the domain of country 2, right? It's entirely about whether country 2 has a credible threat. It is not about how awesome the payoff at the end looks like. It's not what it's about. This is not about whether country 1 looks down the tree and sees awesome things. It's about whether country 1 looks down the tree and sees the wrong decision made by country B. It's not the same thing. It's not about the enticement. It's not about the utility numbers. It's about country 2's preferences and what country 2 is able to do once they have perfect agency, right? So there's a deep interdependence here. There's a very deep interdependence here. It might not seem as interdependent because every time somebody makes a choice in a simple model like this, they're just sort of going left or going right. They're making a choice with complete agency. But they're only doing that conditional on what somebody did in the past or under the expectation of what somebody will do in the future. So even though they're making what appears to be a perfect agency decision, they're doing so in a temporally embedded strategic context. That's the lesson. That's the lesson. You can be done with the video if you want to. That's the lesson. The lesson is time creates different flavors of interdependence. And we as analysts, not just as storytellers, but we as analysts must think that through. We have to think about which of our equilibrium predictions respect the importance of sequential rationality, respect credibility. If you get that, I'm thrilled because that's a really big one. This is a very important point. This is what time does to strategic actors under anarchy. This is what time does to strategic actors under anarchy. It forces them to look down the tree this way. You can imagine this interaction going on for a very long time. Maybe there's a bunch of little challenges that one could make and a bunch of little opportunities for country B to acquiesce, right? But so long as country B didn't want to acquiesce, so long as country B always had a credible threat that whenever we got to the end of time, they would fight. Country A is not going to do well in this. No matter, we can add all the layers you want to. It all comes down to whether country B wants to fight or not. So that's our simple basic notion of deterrence. The idea here is that it is the credibility of my ability to fight back. It is the credibility of my threat to fight back that creates good behavior on country A's part potentially. The most basic notion of deterrence is that Just as somebody doesn't engage in bad behavior because they're worried that they might get punished in the future, this stick idea, don't do bad things because there's a negative injunction against doing that. Here, under anarchy, the negative injunction is just that whoever it is that you antagonize might punch you back. Right? And antagonization under anarchy is a real delicate problem, and it's the problem of deterrence. Now, sometimes you see extended deterrence get mentioned, where it isn't just these two players engaged in this constant threat. I mean, this is interesting. This is a very important lesson, but once you look at it long enough, you realize that the logic of it is so tight that you're not going to be able to put a whole lot of cool things on top of this. I mean, this is an important fact for you to remember. All right? But as a modeling avenue, there's only so many more ways we could go. One interesting way to innovate from here is to say, well, what happens if there are treaties or promises put in place by some third actor who is very strong? What does that do to our deterrence model? And that's the land of extended deterrence, which we're going to discuss in the B block. So let's go to the B block. So we were just discussing the issue of deterrence in a simple sense. So the question is, does one country's credible threat of fighting back, does that introduce enough of a threat that it makes country A not want to do anything nasty in the first place? But there's all sorts of different ways that you can design negative incentives to try to deter bad behavior. In particular, regional powers or global powers are able to use treaties, alliances, and other agreements to try to help to manage some of the little tensions that emerge among other pairs of states. So this notion of extended deterrence, the deterrence that emerges not just from me being tough, but me having tough friends, that's a very important thing to think through. And the question becomes, how does a regional power that is interested in maybe offering a treaty to try to stop a war before it seems like it might get started, how do the associated wrinkles of that decision influence the decision to fight in the first place? So in order to get at that, I'd like to introduce a model of extended deterrence, and then I'll talk about how to analyze it and look for its subgame perfect equilibria. So let's talk about extended deterrence. So this is going to be a pretty big game. It's going to be really complicated, and for that I'm sorry, but I think that you'll see that something relatively simple emerges once we focus only on sequentially rational play. So the idea goes like this. At the beginning of time, some regional power, called them country P. What's going to happen here is country P, the regional power, is observing that country A is thinking about attacking country B. And so they're going to offer country B a peace treaty, a mutual defense pact, to say, hey, we got your back. And then country B can either accept it or reject it. And then no matter what, we'll see what happens between countries A and B. That's the basic idea. So at the beginning of time, the regional power, country P, can either offer or not offer a defense pact to country B. Let's focus first on the world where country P didn't offer that defense treaty. So let's zoom in on that world. So in this world, after an offer wasn't made, then country A can either attack or back down from attacking country B. And country B can either defend against the attack or yield. Now, importantly, we're going to model A and B as if they're simultaneous. So I'm going to use an information set on country B's two decision nodes. And that's going to be the case in every world that we arrive at, as then at the end, the ultima ratio is country A and B may or may not fight a war that is simultaneous move. In general, and there's going to be a lot of endings to this game, lots of terminal nodes. I'm not going to focus too much on any given set of utility numbers. The basic idea is that the regional power doesn't want war. Country B doesn't want war. Country A wants easy war, but not hard war. The regional power doesn't want to get involved in a war that then they've signed up to be part of, and so on. These numbers should all be somewhat reasonable, but the basic idea is actually going to be off the equilibrium profiles. And so don't worry too much about any given set of numbers. The numbers are all a little bit malleable. But here are some utilities. Zoom. And the idea here is that it's country P's utility first. The regional power comes first, then country A, and then country B. So that's this world. So let's zoom back out. We've just pinned down one of what's going to be 3 worlds for us to think about. The world where the regional power doesn't offer any treaties, and then country A and B are just left to their own devices, and a war might happen, a war might not happen. Suppose instead that country P offered country B, the regional power offered the weaker state a defense pact. So let's zoom in. And let's say that if that's the case, then country B can either accept that deal or reject it. They're like, you know what? It would be great to have a strong friend, but I get the sense that you might be wanting more than, that's what happens is you want to have friends that are strong enough that they protect you from other people, but not so strong that then you become beholden to them, right? You want allies that are strong, but not too strong. This is an ancient idea dating back to Machiavelli. If the offer is rejected, if country B rejects the defense pact, then we wind up at another world where country A can attack or back down, and country B can defend or yield. Again, this is as if simultaneous, so I'll give country B an information set over these 2 nodes. All this means is that country B doesn't see what country A does, and therefore country A can't look down the tree because country B is only making 1 choice, not 2. It aesthetically looks like 2, but the information set says, actually, this is just 1 choice. Finally, there's also the world where country A accepted the deal. Or rejected. I forget. They can either accept or reject, and either way, country A can attack. So we wind up with 3 possible wars. The possible war where no offer was made. So that's this world here. Then there's the possible world where the offer was made and was rejected, and then a potential war was fought. That's this world. And then there's the final world where an offer was made and it was accepted, and that's this world. Okay? Regardless, country A can either attack or back down, and country B can either defend or yield. There's an information set. Now, I don't know about you, but this doesn't look especially amenable to backward induction. Find a node. Okay, we have terminal nodes. We have 12 terminal nodes. And each terminal node has some utility numbers. That's great. But how the heck are we going to analyze this thing? None of the decisions that go to a terminal node, all of which belong to country B, those are all part of an information set. And we said that we're not going to break information sets apart. How are we going to analyze this game? Well, in order to analyze this game, I want to introduce a very important concept to you. It's called a subgame. A subgame, as you may have guessed, is part of the game. In particular, a subgame is a subset of the game's nodes that have to obey, that subset has to obey certain rules. What are those rules? Well, for starters, it can end only in terminal nodes. So we're not going to look at a subgame that happens only like halfway through and then doesn't get to the ending. So any subgame has to end only in terminal nodes. 2, a subgame cannot tear an information set apart. Right? So I can't break one information set into 2 separate subgames. Anytime there's a decision node in that subgame, so too must every other decision node in that information set be in the subgame in question. You'll see in a second. This is all easier than it sounds. And 3, there has to be a root node. There has to be a first move. It can't be like a first information set. There has to be a first move in any given subgame. Okay? So this game, as we've drawn it, has a number of subgames. And we're going to try to figure out what that number is. Notice that because every terminal node is immediately preceded by an information set decision node, right? So we're not going to tear any of those apart. So actually, the smallest subgames in this game are the ones that start with country A's decisions. A can attack or back down, and there are 3 of those. And this creates 3 subgames. the subgame where A can attack after no offer was made, the subgame where A can attack when an offer was made and was accepted, and the subgame where A can attack after an offer was made and was rejected. Those are our 3 smallest subgames. Why is it smallest? They don't have any subgames within them. If you went any smaller, you'd violate one of the rules of a subgame. You'd have to tear an information set apart, or you'd have to end in something other than a terminal node, or you'd have to get rid of a root node. These are the 3 smallest subgames. There's a 4th subgame, which begins from country B's decision about whether to accept or reject the offer if one is made. So that's our 4th subgame. It starts with B's accept-reject decision. And finally, there's a 5th subgame, which is the entire game. The entire game is always a subgame. Just the same way that a set is a subset of itself. So we've identified 5 subgames. The 3 war decisions, essentially. Country B's decision about whether or not to accept the offer, and Country P's decision about whether or not to make an offer. So what we're going to look for, instead of backward induction, we're going to generalize this a little bit. We're going to go looking for subgame perfect equilibria. What's that? A subgame perfect equilibrium is a strategy profile where every strategy chosen is a Nash equilibrium, not just in the entire game, but in every subgame. What we're saying with subgame perfection is what's happening in small worlds, what's happening in the tiny subgame decisions, what's happening in the future, like some small hypothetical world, what happens there has to complement the decisions made in the entire game, so that early decision makers are looking down the tree and looking for Nash-like behavior. Now, if there aren't any information sets, that's easy. You just look for what's sequentially rational. What is the best decision by everybody at a given node? But here, in information set land, we have to think a little bit harder about Nash behavior if there are potentialities for simultaneous moves, or as-if simultaneous moves, as we have here. So we need to look for Nash equilibria for each of the subgames, and try to find appropriate combinations of those in a way that ultimately creates something sequentially rational. You'll see what I mean here in a moment. So we're essentially doing backward induction here, but instead of looking only for decision nodes that end in terminal nodes, we're looking for subgames that don't have any smaller subgames. And that's going to be our endings. We're going to solve the endings, then we're going to go up a step. We're going to solve up a step, and then we're going to go up another step, and so on. It's backward induction, but where the unit isn't decision nodes, the unit is subgames. So there are 3 smallest subgames in this game. Those are the 3 small subgames that I mentioned before, where Country A is making its decision to attack or back down, and Country B is making their decision about whether to defend or yield. So let's zoom in on the subgame that occurs after no offer was made. Zoom. And let's convert it to a matrix. Zoom. And let's look for the Nash equilibria. I'll just put in some stars. You'll notice that this game has a unique pure strategy Nash equilibrium. And in that equilibrium, Country A attacks and Country B defends. And that yields 0 happiness points for the regional power. They're not happy that a war happened. 2 for Country A. They got to attack somebody that didn't have a friend. And 1 for Country B. Okay? So that's this game, this subgame is now all the way solved because there was a unique prediction here. This subgame is solved. It's as if this subgame was never here. We can just write in 0, 2, 1 here because that's what would happen. The only plausible outcome here, the only sequentially rational thing here is for that to be the simultaneous move issued by countries A and B. Now let's shift over to the world where Country P made the offer and it was rejected. Let's go to this middle subgame. So we zoom in on the subgame and we write it as a matrix. We put in some best response stars. Notice, this game has 2 pure strategy Nash equilibria. There's the one where country A attacks and country B defends, which yields -1 for the regional power. They're not happy that a war happened. 2 for country A and 1 for country B. And there's the world where there's also a Nash equilibrium where country A backs down and country B yields. 1, 1, 3 are the associated utilities. So we now consider this solved, but we have to consider the possibility that either equilibrium is plausible. And we're only going to focus on pure strategy, so don't worry about the mixing. We're going to say, okay, either of these two equilibria is plausible, and we need to think about how combinations of this are going to emerge. There was a unique equilibrium in the world where no offer was made. Now there are two. Okay? The attack defend and the back down yield. Finally, let's move over to the smallest subgame that occurs after an offer was made and was accepted. And let's convert it to a matrix. Again, this game has two pure strategy Nash equilibria. The one where country A attacks and country B defends, and the one where country A backs down and country B yields. And those have respective utility imputations -2, 2, 0, and 2, 1, 2. So we've gotten rid of some of the possibilities. We've said some of these things don't seem like equilibrium play once we get down to brass tacks and country A and B have to make their simultaneous decision. So we consider all these solved on the understanding that two of them have multiple possibilities. There are 4 combinations of equilibria in the smallest subgames. Notice that no matter what, in the world where an offer wasn't made, all that happens is attack defend. However, if an offer is made, then either of those two worlds, it might be an attack defend equilibrium or a back down yield equilibrium. So it could be attack defend in both, back down yield in both, or one or the other in either way. We're gonna have to consider all 4 of those possibilities, but right now there are 4 possible combinations of equilibria among these. We're gonna have to consider those all as separate cases. It's just a little bit annoying in terms of keeping track of the cases. So now we look for a subgame that contains no other subgames, on the understanding that the subgames that we've solved are now solved, right? So for example, the entire subgame, the game that is the subgame that's the entire game, still has a subgame that's smaller, Country 2's decision about whether to accept or reject. However, Country 2's decision about whether to accept or reject is followed only by solved things. So let's focus in on that decision. Well, now whether Country 2 wants to accept or reject depends on which pairs of equilibria emerge in these two worlds, right? So for example, suppose that we were playing the attack-defend equilibrium in both worlds. Well, the attack-defend equilibrium when you accepted gets you 0 happiness points if you're country B, and the attack-defend equilibrium if you rejected gets you 1 happiness point, so you would rather reject. Similarly, if you were expecting attack reject in accept world, but back down yield in reject world, that gets you 3 happiness points now. Well, you would rather reject and expect to see a back down yield there. However, if you were expecting back down yield in the accept world and attack defend in the reject world, then you would rather accept. You'd get 2 happiness points instead of 1. Finally, if you were expecting back down yield in both worlds, then you would rather reject. So in other words, Country B would like to reject unless they feel as if accepting is the thing that creates back down yield in this world. So if it's plausible that that would influence equilibrium selection that way, then they would rather accept the deal, otherwise they reject the deal. Okay? So we now consider that decision node solved. We've solved 4 of our 5 subgames, all of the little ones, plus now this extended one where Country B was making this decision about whether to accept or reject. The question now becomes whether the regional power would like to offer this deal at all. No matter what happens, if an offer isn't made, if they decide not to offer, then they have a unique thing to expect. They should expect 0 there no matter what, because we get to attack defend in the subgame where there was no offer. Country A attacks and Country B defends, and that gets the regional power 0 happiness points. However, if they accept, we've got 4 combinations to think about. we've got 4 combinations of equilibria to think about. Suppose that there was an attack-defend equilibrium played in both worlds, in both the accept world and the reject world. Okay? If that were the case, then we also know that country B would rather reject. They prefer the reject AD to the accept AD. If that's the case, then country P would expect to get -1 happiness points if they make the offer. If they make the offer, it will be rejected, the AD equilibrium will be played, and country P will expect -1 happiness points. They'd get 0 if they didn't make an offer. So if that's the case, they would rather not offer. Don't offer on the expectation of rejection, attacking in the accept world and attacking in the reject world. That's a subgame perfect equilibrium. Everything is in equilibrium in its respective subgames. Attack defend, if accept an offer that's made, is all equilibrium. Attack defend if reject, then don't offer. This is all complementing one another. You can visualize it in the tree. However, the analysis is actually far deeper than just what you may have surmised from the tree. So backward induction is very intimately related to the tree. But subgame perfection is about thinking through some of these equilibrium contingencies as the tree is growing. It's not just go to the end and work backwards. It's go to the end and then think about how this one ending relates to another ending. There's all sorts of choose your own adventure stuff at work here. So in this equilibrium, let's think about how to write it down. Because what we need a strategy for every player. So we need to know, what will country P do at their 1 decision node? What will country A do at their 3 decision nodes? What will country B do at its accept reject decision node? And what will country B do at their 3 information sets if after country A moves? So we need to know a lot of things. So what's happening here? Well, country A is not offering. They don't offer. In the world where offering doesn't happen, country A attacks and country B defends. That's the equilibrium path of play. The equilibrium path goes, don't offer, attack, defend. However, what happens off the path has to complement what happens on the path. So in this now hypothetical counterfactual world, where country P made an offer, what happens? At the next decision node, country B rejects the offer. If an offer had been accepted, country A attacks and country B defends. And if an offer is rejected, country A attacks and country B defends. So this checks all of the boxes I just discussed. Everything is a Nash equilibrium in its respective nest of subgames. We wind up with a subgame perfect equilibrium. However, that's not the only one, because we have these other combinations to think through. So suppose instead that if an offer is accepted, we play the attack-defend equilibrium, and if an offer is rejected, we play back-down yield. Well, we already agreed that if that's the case, country B would rather reject the offer again. So country B rejects, then attack-defend if accept, and back-down yield if reject. That gets the regional power 1 happiness point, so now they like that more. That 1 happiness point that they get for the equilibrium that ends up happening, they prefer that to the 0 happiness points that they get in the world where they don't make an offer. So here's another subgame perfect equilibrium. Country P makes an offer. If an offer was never made, country A attacks and country B defends. If an offer is made, it is rejected. If the offer is accepted, then country A attacks and country B defends. And if the offer is rejected, then country A backs down and country B defends. Now the equilibrium path of play goes from the beginning of time, country P makes the offer, country B rejects the offer, country A backs down, and country B yields. That's the equilibrium path, but everything that happens off the path has to complement what happens on the path. Notice that when I describe these strategies, these sound like computer programs. We're describing ifs and thens about all sorts of contingencies, many of which don't happen. You can imagine this tree being something that we show to players who then have to submit an envelope saying what they would do at every chance they had to do something. Right? It's all a bunch of contingencies. We need complete contingency plans. A subgame perfect equilibrium tells us everything that happens, whether it actually is realized or not. There's another pure strategy subgame perfect equilibrium. Consider the combination where if the offer is accepted, it's back down yield, and if the offer is rejected, it's attack defend. Well, we already agreed that if that's the situation, then now country B is going to accept the offer. Country B accepts the offer, which then yields back down yield. Right, so the idea here is that they prefer to accept if it's the thing that is decisive in terms of a backing down happening. The associated equilibrium gives the regional power 2 happiness points, which again they strictly prefer to the 0 that they get in the world where no offer was made. So we have a third subgame perfect equilibrium. And in that subgame perfect equilibrium, country P makes an offer, which is accepted. In the world where no offer was made, it's attack, defend. In the world where an offer is made and is accepted, it's back down, yield. And in the world where an offer was made and it was rejected, it's attack, defend. It's all about these equilibrium combinations. Multiplicity of equilibria. If I was going to watch you play a game that had multiple equilibria and then try to condition what I wanted to do today on what might happen then, how the heck do I know which equilibrium of the game with multiple equilibria is going to happen? If I'm betting on who's going to win chicken, and all I know is that in the game of chicken, one of you wins and one of you loses, how do I know which equilibrium is the equilibrium that you play? Similar here. Multiple equilibria creates a lot of interesting wrinkles about how to look down trees. There's a fourth subgame perfect equilibrium. Suppose that it was back down yield at either of the possible nodes after an offer was made, accepted or rejected. Well, if that's the case, then we decided that country B would rather reject. And that yields an equilibrium of 1 happiness points for country P, which again strictly beats the 0 that they get at the world where they don't make an offer. So, here's your final pure strategy subgame perfect equilibrium. Country P makes an offer. That offer is rejected. In the world where no offer was made, country A attacks and country B defends. In the world where an offer was made and was accepted, country A backs down and country B yields. Chewie says hi. And in the world where an offer was made and was rejected, country A backs down and country B yields. It's all about these combinations. So the answer about whether one of these treaty offers is useful, the answer is it depends. It depends on which equilibria we think are likely to emerge once we get down to brass tacks with some of these actual contingencies where A and B have to make their final decisions. But the idea here, the overarching idea here is that because you don't want an ally that's too strong, because you just as soon do this yourself if you could. So the idea here is that, whether or not this deal has any bite, whether or not it's a deal that would want to be accepted, that depends on whether or not it's going to be decisive. And whether or not it's decisive depends on which equilibria we think are likely to emerge. So subgame perfect equilibrium takes seriously the idea that we have to think about all the equilibrium combinations, right? And when we have to make our bets about that, here country P is making a bet and country B is making a bet. Bets are being made. They're having to make decisions about what they expect to see in the future, but that's a lot more nuanced than it was before, right? So extended deterrence comes down to whether or not acceptable offers are decisive. If they're not decisive, why would you accept them? So this model, it's a little bit tricky. The next one's going to be a little bit easier. I just wanted to show you that if you take this simple concept of deterrence, which is very backward inductionable, and then add this one wrinkle of extended deterrence, which then requires us to go from backward induction to full-on subgame perfection, you wind up with a really rich tapestry of possibilities that depends on which equilibria we think are likely to emerge. And this really highlights the importance of the complete contingency plan in analyzing a model of this type. you don't just write it down and you don't just start making some of the edges red. There's a lot more to it than that. You have to think through each of the possible worlds that could emerge and what strategic possibilities emerge within them. So I want to do one more example of this. It will be exactly the same. I just want to show you how the rule of law game ends, which will be in the C block. Let's go to the C block. So here in the C block, I want to show you a little bit more about how credibility and equilibrium emergence influences look-ahead politics, but in the domestic context rather than the international one. So again, I want to talk about the role of states. And the reason we keep talking about the role of states is, under an international anarchy, there are benefits of order that we don't have at the international level that we do have at the domestic level. And one interesting question is, well, why did we stop, or have we stopped? And one reason to think about the role of the state isn't just to think about what the role of the state is, it's to think about what we don't get from having a world state. What are the benefits that we forego by not having a world state? Or what are some of the advantages of not having one? What are some of the downsides of order? So the reason we keep talking about the role of the state is it helps us to understand anarchy better. Okay? Before you think that I'm just not trying to... It's a very important question in international relations, even if it isn't immediately obvious. And the reason it's important for IR is we don't know what disorder is if we don't know what order is. We don't know what order is unless we know what anarchy is. I mean, there's all sorts of interesting tricks among all these concepts. Regardless, let's queue up a somewhat extended version of the rule of law game. So the idea here is that now the two factions, A and B, will be able to coordinate on throwing the ruler out either way. So let me call up the rule of law game as I drew it last week. And you'll remember that in this version, remember there's a sovereign at the beginning of time, and the sovereign can either transgress the people's rights or not transgress. If they transgress, that gave the people an opportunity to coordinate. They could either both acquiesce to the transgression, challenge, or some combination, and they needed to both challenge in order for to throw the sovereign out. However, now let's extend the model so that if they don't transgress, it doesn't go to the status quo. Instead, it goes to some other opportunity to coordinate. Again, they can challenge or acquiesce just as before. The only difference is that now the sovereign only gets 2 happiness points, and the people are thinking about whether or not to have 8 happiness points for not challenging, or 7 if they both challenge. And again, we'll have an information set there. We're not going to tear that apart. So this game has 3 subgames. The first subgame starts at Faction A's decision about whether or not to challenge or acquiesce after transgression. The second subgame is Faction A's decision after non-transgression. And then the third subgame is the subgame of the whole. So just as before, I'll convert these 2 games into matrix versions. Notice that in the world where the sovereign transgressed, there are 2 pure strategy Nash equilibria. There's the one where both factions challenge, and there's another one where both factions transgress. Sort of like a stag honey sort of thing there, right? Because one of them is better than the other. The respective payoffs for the sovereign can either get 8 if in the equilibrium where they both acquiesce, or 0 in the equilibrium where they both challenge. However, if they don't transgress, in this subgame, we wind up with only one pure strategy Nash equilibrium, the one where they both acquiesce, because they have nothing to challenge against. So again, this might as well have been a terminal node. And what I want to show you is that which equilibrium we think is likely to emerge in the world where the sovereign transgresses is what's going to determine whether or not the sovereign transgresses. So consider first the situation where the citizens, if transgressed upon, both acquiesce. That's equilibrium play. So if they both acquiesce, they both get 2 happiness points. And the sovereign gets 8. They're really happy. If the sovereign didn't transgress, the only equilibrium payoff they could expect is 2. Well, that 8 beats that 2, so they would rather transgress. Here's subgame perfect equilibrium number 1. The sovereign transgresses, If transgressed upon, both factions acquiesce, and if not transgressed upon, both factions acquiesce. However, there's also the equilibrium possibility that if the sovereign transgresses, it could be that they get challenged upon, both factions challenge. That's bad, because now the sovereign would get 0 happiness points. So they begin comparing that 0 that they get for the challenge to the 2 that they get for the acquiesce after they don't issue a transgression. So in that world, there's another subgame perfect equilibrium. There's 2 subgame perfect equilibria. And in this second one, the sovereign doesn't transgress. If transgressed upon, both factions challenge, they deter the sovereign. And with no transgression, mutual acquiescence again. So look, these are 2 very different subgame perfect equilibria. In one, there's transgression and acquiescence. In another, there's no transgression at all. This is a deterrence model just like the first one. These models are all about deterrence. It's just that the question isn't just about whether one country rocks up to another country and starts a fight. It's about whether or not a mutual defense pact is offered. It's about whether or not sovereigns transgress upon their citizens. These things are all the same. Credibility is everywhere. Now this one is kind of simple and straightforward. I just wanted to show this to you because on your problem set, you're gonna have to do a more extensive one that has like 4 possibilities, where we're going to allow the politics to become even a little bit more nuanced. But I just want you to think about combinations, about equilibrium combinations. When you make a choice, you let people play a game. And when you let people play a game that has an indeterminate outcome, in the sense that there's multiple equilibria, when you let them do that, you have to think all the possibilities through. You know, it's not just a matter of thinking that the one best thing for you is going to happen every time. It might not. If you're the sovereign, there's a chance you're going to go up to the to the challenge equilibrium. If you transgress, you might get challenged. That's no good. You have to think that through. Now, what are the factors that determine that? Anything. I mean, it could be whether or not the 2 factions speak the same language. It could be whether or not the 2 factions have good historic ties. Have they been fighting one another? Do they use the same currency? Are they in the same part of the country? All the things that tell us whether coordination is possible. Because here, all they have to do is be able to coordinate. Now, the wrinkle that we're gonna add to the model is, what if you're allowed to transgress against one of the factions while you buy the other one off? That's pretty fun, right? But in all of these, it's a matter of credibility. It's about whether there are threats off the path that make you do good things. And the answer to that is it depends. Now, in a simple, straightforward, simple deterrence model, it's a matter of thinking through one decision node, right? If country A challenges country B, then country B has a node to make it. It's not a very complicated decision. But life isn't always that easy. Sometimes you have to think through how mutual actors will respond to your choices in equilibrium ways. How will they use Nash after you've made a choice that influences their Nash behavior? That's heavy, right? This isn't a technical lesson. None of this is math. This is about something much deeper than that. This is about not just how rationality aggregates. So up until this point, we talked about what is rationality? How does it aggregate? Both social theory and game theory, simultaneous move game theory. Now it's not just how does rationality aggregate. Now it's how does rationality aggregate and unfold over time? These simple, straightforward models, the active analysis with them is itself instructive in ways that weren't the case just for Nash, I don't think. You know, learning how to put asterisks on best responses or learning how to think through a profile. Yeah, you learn a lot from that, but not the same way. You get a deeper kind of learning from the active analysis here than you did in the previous style of game theory we were talking about. You learn more from doing here than you did before. So today we talked about how we as analysts can begin to interact with these time-respecting fables that we write down. And we realized that, whether it's two states under anarchy or two factions under the rule of a sovereign or two smaller states thinking about how to behave under the umbrella of some regional power, no matter what, there's a lot of interesting nuance about how rationality aggregates into subgame perfect equilibrium, and how the role of the future, the shadow of the future, the hypothetical worlds of the future shape your decisions today. So I stand by my provocative thought from last week that time and strategy are hard to think through in a causal way. And in the absence of that, there's indeterminacy problem for how we as international relations students ought to think about how countries behave over time. However, today's analysis suggests that at minimum, we can whittle the set of future possibilities down to only those possibilities that represent Nash-like play in the respective new time presence that they take place under, right? So if I make a decision, then some present happens, and something Nash-like will happen in that present, and I have to think about that. If I make another choice, then something else, then some other present will emerge, and some other Nash-like behavior may emerge in that alternative present, right? So when I want to think through, when I'm making my decisions now, how do I think those through in a way that respects the fact that whenever I get to a new present, something Nash-like will happen, or something will be made by another decision maker that has just as much foresight as I do. And it's with that idea of foresight in mind that I'd like to conclude with a provocative thought. So in all the models we've discussed so far that respect time, there's an end of time, right? There are terminal nodes everywhere. We even said that we could define utility functions on the terminal nodes. Now, that suggests that the players that we've been modeling have a sense about when the end is, right? So whenever that end time is, that end of days, that very last moment, they go to that last moment, they solve that moment. They go to the moment just before, they solve that moment on the understanding that the last moment has been solved. They go to the moment before that, and they solve, and so on. The backward induction algorithm then says, once you've gotten to the ending, solve it and go up. Well, that all sounds great. Let's take a poll of all of the heads of state in the world. Let's take a poll of them and ask them when they think the last day is going to be. It's an interesting question. When do you think should be the last day? When is the terminal node? When is the last day? What's the last day? We've been very cavalier just putting terminal nodes everywhere, but we've said, and that's the end of time, and that's the end of time, and that's the end of time. When's the end of time? Now, that might be a faith thing, that might be a science thing. Which science thing? It might be when you think that the universe runs out of expansion or something like that. It might be like when the sun runs out of fuel, and there's all sorts of different ways to answer in a scientific sense what's the end of time, not to mention all the potential religious answers to what's the end of time. And I'm sure there's some answers I'm not thinking of because this is way over my bald head. I have no idea what I'm talking about. But I do know that if I have no idea what I'm talking about the end of time, then it's an awfully bold thing for me to do to put terminal nodes everywhere in these games. Because I have no idea when the ending is. The idea of credibility and commitment means that there's always a chance to not live up to an ending. We write down a contract. I live up to it today. I live up to it tomorrow. I live up to it for 10 years. I live up to it for 1,000 years. And then I might not live up to it. Every day was a chance for me to not live up to my deal. It wasn't just that I signed it, I lived up to it once and that was a terminal node. Right? This is why backward induction can only go so far. Because not every style of analysis, not every style of time-respecting model we write down will have guaranteed endings, will have ends of time like that. But we just saw that what counts as credible, what counts as reliable, what counts as sequentially rational, depends on having a sense about what will happen at the end of time at the smallest subgame or the final decision node or whatever, solving it and then working backwards. Now, that seems like a perfectly reasonable way to proceed. I'm sure you nodded some of the time. It seems like a good way to go in time-respecting models that have endings. However, we don't always know when the ending is. Now, the fact that we don't know when the ending is doesn't mean that we can't write down models with terminal nodes, okay? It just means that we need to also have the opportunity to write down games that don't have terminal nodes if we need to. They can go on forever. Not because we think they're actually going to go on forever, but rather because we don't know when the ending is. And so the only way for us to proceed like that is to model as if they went on forever. But this is difficult. That's a difficult thing to think through. What would haggling look like if we could repeat our offers forever? I'm buying a car from you, and we're haggling over the car. I think it's worth $10 and you think it's worth $20. It's a really nice car, apparently. Now suppose that I made an offer and you rejected it, and you counter-offered, and I rejected it, and I counter-offered, and you rejected it, and I counter-offered, and so on. I mean, eventually, business hours will end that day. We'll get to 5 or 6 o'clock or whatever, and I'll want to go home and watch Masked Singer, and they'll want to go home and have their TV dinner. They'll want to go home. But let's say that we just kept going. Let's say infinite time horizon. So we just kept haggling. We're still haggling. It's midnight. I'm haggling with you. We're sitting in the middle of an empty car dealership and we're haggling. Tomorrow we do that. The day after we do that. For a whole year we haggle. We haven't gotten up from the table. Things have happened. My beard is down to here. We're still haggling. I think it's worth 11. How about 19? How about 11 plus epsilon? How about 19 minus epsilon? And so on. We're just haggling over time. Infinite horizon, not because we think this is actually going to go on an infinite amount of time, but because we don't know when the end of time is in this particular interaction. Well, we just keep going. Boom, 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 boom. Let's imagine all the things that political people do when they do this sort of thing. We self-impose a deadline. We say we must come to an agreement by the end of business on Friday. And then it's Friday afternoon and we're still haggling. Bump, 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 we're still haggling. We just run right through that deadline. That deadline is incredible. Or else what? Or else what is the answer? The only reason that deadline would have any bite is if there was a reasonable or else what at the end of it, as you learned today. The only thing that stops you from doing something is a good or else what. So we're still haggling. The dealership is closed. 3 generations of Rodneys have run this place, and they finally decided to close their doors because car dealerships don't make any money anymore. Nevertheless, you and I are still haggling over this car. Infinite horizon. We're still haggling. What counts as credibility there? In a world where after the zombie apocalypse, you and I can still be sitting there emaciated, having eaten nothing but those little Lance crackers that they have at car dealerships for a Google years. Thankfully, those things probably last more than a Google years, thanks to the preservatives. What counts as a credible threat? What counts as a reasonable or else then what? How are we going to understand the future when it doesn't have an ending necessarily? That's where we're headed. That's in 2 weeks. And when states interact, they do so with long time horizons. States don't die. So presumably, the end of the haggling would be whichever of us died first in a biological sense. And even then, my ghost would come down and say, hey, how about 12? States don't die that often. States don't know when they're going to die. I know I'm going to be dead in the next few years. Or that's some number, right? States don't know that. States don't know that. States don't know they're going to die. Time means a completely different thing for them. Endings means a completely different thing for them. So even though we talked a lot today about how to tell the ending of finite stories, some stories have no ending. How do we tell stories about them, and how do we end those stories? It's an important theme to think about in these final few weeks of the class, because stylized time is really useful, not just because it's a little bit more simple than clock time. It's useful because it allows agents with different conceptions of time than we humans have to be able to experience time. That's kind of weird when you think about it. One thing that's going to be really remarkable is that subgame perfection, our method about thinking about sequential rationality, is going to very easily be able to address infinite horizon situations, where even though all of the relevant flesh and blood actors would have been long dead by the time we get to the ending, quote unquote, the institution that persists will still be able to be modeled. I think this goes to show that time is a lot more than what you and I think it is. And therefore, sequential rationality is far deeper than what you and I might be able to appreciate at a prima facie level. It's a heavy thought to end on. That's a really heavy thought to end on, but I think it shows that the things that we're studying are abstract enough that we don't have to encumber ourselves with these very human ideas about these things. That's stupid. It's a really heavy thought to end on, but I think it goes to show that time is all around us in ways that we don't fully understand. But if we think hard about it, those things that we think that we know about time and credibility and sequential rationality are very malleable. I can't wait to show you that in the next few weeks. Thanks for watching.